Okay, today we shall see the input and output resistance of an amplifier. Now, if you take an amplifier, okay, so we can consider this as the input of the amplifier and this as the output of the amplifier. Fine. This Rin is the input resistance and Rout is the output resistance. And when we see these input and output resistance, we see these across the two terminals here. These are called the input terminals and these are called the output terminals. And across those input and output terminals, we see this input resistance and the output resistance respectively. See, that is what is the figure showing. Fine. What is input resistance then? If you have to give it as a definition, input resistance is the ratio of input voltage to input current. It is expressed in ohms. Input voltage to input current. What is input voltage here? That's not written. Okay, so that can be shown here. See here, this is the input voltage. Understand? And this is the input current, I in. And what is input resistance as they tell us? Input resistance is, suppose Ri is there. Input resistance is the ratio of input voltage V in by the input current I in. So this is input current and this is input resistance and this is expressed in terms of ohms. Understand? So this is what you're able to see here. That is what is input resistance, and it is the ratio of input voltage to input current, and it is always expressed in terms of ohms. Now, the input of an amplifier is normally purely resistive. This would normally be purely resistive. That means reactive component could be negligible. What is reactive component means? Anybody? What is reactive component they are talking about? See here, instead of Ri, we can even talk about Zi. What is Zi given by? Zi is Ri plus J Xi. Fine. Now, what is Ri and what is Zi? Can anybody tell me? What is Ri and what is Zi? Zi is the impedance, mind you. This is the impedance, whereas this is the resistance. Understand that? The input of an amplifier is normally purely resistive. Any reactive component is negligibly small. That means if see here, if this Xi, this is the reactive component, this is the resistance. Anyways, Ri is the resistance, and this Xi is the reactance. It's called as reactance, this Xi. And this reactance is very negligible most of the times. Understand that? So in that case, the input resistance is purely resistive. Okay, it's not the impedance. You understand now? When Xi is negligibly small, when this Xi is negligibly small, Zi is Ri, then the impedance is purely resistive. Most of the times it is like this. Understand that? Now, in some cases, the reactance of the input may become appreciable. Appreciable means what? Sometimes this would be very large. Appreciable means this would not be negligible. This would be appreciably large. So in such cases, we would refer to input impedance rather than input resistance. So in such cases where Xi is large, there we rather don't consider R in. We don't rather refer to this as the input resistance, but rather refer to it as Z in. That is the input impedance. So is what they are telling us. Is that okay with you now, everybody? So this is simple. Okay, input resistance is what, and output resistance is what we are seeing. So input resistance is the ratio of input current, input voltage by input current. Understand this? And this is normally in ohms. Fine. And this is purely resistive because the reactance part is 0. Okay. And if this reactance part is not 0 and if it is appreciably big, then in place of R in, we rather consider Z in, that is the input impedance. That is what is being told here. In some cases, the reactance of the input may become appreciable. That means it may become large. Okay, so in such cases, we would rather refer to input impedance rather than input resistance. We refer to this as input impedance rather than input resistance. So we will be rather mm, denoting it as Z in such case. Understand that? So that is regarding the input resistance. Now let's see what is output resistance. Yeah, output resistance is the ratio of open circuit output voltage to short circuit output current. Now, what is open circuit voltage and short circuit current is what we have to be seeing. Now, everybody should understand this. What is open circuit voltage, open circuit output voltage, and what is short circuit output current? So here when in input impedance, we were very simply, we were dealing with the input voltage and the input current. You have to see this cursor or the pointer that I'm moving on the slides here for the reference. Is everybody able to see that, the pointer? Okay, so this pointer is what you should be seeing. This input resistance is the input voltage divided by input current. It was quite straightforward. The input current flows here and the input voltage drops across these 2 points. And the ratio of voltage to this input is Rin, is what we saw. But in output resistance, we are talking about two different entities here. What is that? Open circuit voltage to short circuit output current. Open circuit output voltage and short circuit output current. See here, this is open circuit output voltage. Open circuit means what? Here you see these two terminals. See these two terminals. So these two terminals, okay, are open circuit because there is no current flowing here. They are open circuit. Understand? The same terminals, for example, here I'm writing the same figure here. Okay. Now, if the same output and input, these output terminals are shorted, I'm shorting this. Okay, and there will be a current that is flowing, that is called as I out. This is called as short circuit output current. Everybody understand that this is open circuit output voltage when these two what terminals are open, that is open circuit output voltage, and this is short circuit output current. Understand that? So we can maybe in particular we can say open circuit output voltage and this is short circuit output current. So we can write the output resistance R out as open circuit output voltage divided by short circuit output current. Understand that? So this is what is the output resistance is all about. Output resistance of an amplifier is. Okay. Note that this resistance is internal to the amplifier and should not be confused with the resistance of the load connected externally. Sometimes we connect load right across these 2 points. We connect load, and that is called as RL. And that RL is not this output resistance. This output resistance is internal to the amplifier, is what they are saying. The output impedance or the resistance is internal to the amplifier and it should not be confused to the load resistance that we connect across these 2 points, is what they're saying. That it's the internal resistance of an amplifier. Fine. As with the resistance, the output of an amplifier is also normally purely resistive, and the we can safely ignore the reactive component. If the reactance is big, we should consider the output impedance instead of the output resistance. The same thing. Okay. If reactance is small, it is purely resistive, and we rather neglect the reactive component and say it is input resistance. Nor similarly here, if the reactive component is very small, we call it as output resistance. If the reactive component is big, then we call it as output impedance. Okay, so that is what they are telling us. Is this okay with you, everybody? Do you have anything to ask me here? Do you have anything to ask me? No. If you have anything, you can ask me now. Because they're all very small portions. Okay. The next topic. That's Okay, now one more thing that they are saying. Finally, it's important to note that although these resistances are meaningful in terms of the signals present, they cannot be measured using the conventional meter. I've told you they're all internal to the amplifier. They cannot be measured with the multimeter or conventional meter means multimeter or voltmeter or ohm meter. Okay, using that only we have to we cannot rather measure them using the conventional meter. Conventional meter means you should understand. Okay, so we use something called as multimeter. What for multimeters are used? They can be used to measure voltage, they can be used to measure current, or they can be used to measure the resistance. Okay, do you know what is this multimeter called as? If it is only measured, if it is only used to measure the voltage, it is called as
Voltmeter.
voltmeter. Then here it is, if you are measuring the current,
Ammeter.
ammeter. Very good. It is called as ammeter. And if it is resistance, it is called as ohm. We call it as ohm meter. Voltmeter if it is voltage, ammeter if it is current, ohm meter if it is resistance. Okay, so conventional meter means it could be a multimeter which is used to measure any of this. Fine, but using this conventional meter, we cannot measure the input impedance or output impedance, is what they are saying. They are internal to the amplifier and they cannot be measured using any of this, is what the statement is telling us. Is that okay with you? Now, with that, let's move on to something called as the frequency response. Now, you should remember the different types of amplifiers that we have discussed in the class. We have discussed AC coupled amplifier, DC coupled amplifier, wideband, radio frequency amplifier, audio frequency amplifier. Remember all that point? Okay. Now, what is the difference between AC coupled and DC coupled? Do you remember? What is the difference between AC coupled amplifier and DC coupled amplifier? Anybody? In AC coupled, in AC coupled,
No DC will be.
Only AC is coupled,
only
sir.
AC is coupled to the next stage. Whereas in DC coupled,
AC plus DC.
along
Both
with
AC and DC.
DC is also coupled. What is AC and DC means? AC means there is some frequency. DC means there is no frequency. Understand that? Now, why I'm discussing this is because I'm discussing the frequency response. Frequency response means, okay, the frequency response shows what all frequencies are there in an amplifier, or an amplifier is amplifying some frequencies, right? In AC coupled amplifier, what is that it is amplifying? In DC coupled amplifier, what is that it is amplifying? And in wideband, what it amplifies? In radio frequency, what it amplifies is what we are looking at. Okay, so now just understand here, we have something called as DC coupled. See this line now, everybody? See the line that I'm showing you here. This is the line. Okay, so this is called, this is the frequency response of DC coupled amplifier. This, okay, and it amplifies all the frequencies which is there in that particular signal. Which is that signal? That signal is AC as well as DC. See, except all the amplifiers, this DC coupled amplifier is starting at 0. Is that okay with you? You're seeing this? Yes? Everybody is able to see this? It is starting at 0. The frequency has to be 0 here. The frequency is 0. The gain is 1. Here the gain is 1 because they are going for logarithmic scale. I'll talk about what logarithmic scale is, but understand this x-axis is frequency and this y-axis is gain. Understand that? Now, in this y-axis and x-axis, whatever we have, as the frequency is varied, how the gain of the amplifier varies is what it is showing. Except for all other amplifiers, only for this DC coupled amplifier, something that I've marked in red now. Okay, for this DC coupled amplifier, the response starts from 0. Even for 0 frequency, there is some output, there is some gain. So that means that gain which is there at 0 hertz is the gain that it is giving for DC signal. Get that point? So for DC coupled amplifier, it is AC as well as DC. So there will be some gain even for 0 hertz. DC means 0 hertz. Here, that's why these are all in hertz. Here, frequency in hertz. So this is 0 hertz. So we have some output at 0 hertz also, and that happens only with DC coupled amplifier and not with any of the amplifiers. What is this frequency response? Now you understood? Frequency response is the output of an amplifier for different frequencies. Output of an amplifier for different frequencies. We go on varying the frequencies and we see the response of that particular amplifier. If that response of the amplifier exists even for 0 hertz, okay, then it has to be for DC coupled amplifier and cannot be so for any of the other amplifiers. Understand? Then we have this audio frequency amplifier. What is this audio frequency? I've told you what is audio frequency in the class. What is audio frequency? Anybody? Audio frequency means audible frequency range. Where it ranges from? It ranges from 20 hertz to 20 kilohertz. See this audible frequency range now. So here it is. So it is somewhere here. It is means it is this solid line. You see this, right? This solid line. Let me now bring that with the red line again. So now I'm talking about this. Okay, the solid line which I'm drawing now is for audio frequency amplifier. Fine. And audio frequency ranges from 20 hertz to 20 kilohertz. I've told you, isn't it? Now see this here. It's almost from 20 hertz to 20 kilohertz, or a little more than that, somewhere here. 20 to 20, somewhere here. Okay, so this is audio amplifier. And what is this audio amplifier doing? Audio frequency amplifier doing? It is amplifying only the signals only the frequency components which ranges from 20 hertz to 20 kilohertz. Rest all the frequencies, it is what is doing? It is, we say it is attenuating. It attenuates all the frequency components except the audio frequency components. That means we'll have the gain only for audio frequencies, and for all other frequencies there will not be any gain. Is that understood now? Yes, everybody? Fine. Now, if you go with wideband amplifier, this I told you its range is very big. It ranges from, say, somewhere here. It is ranging from 5 hertz or 50 hertz somewhere here, and to 10 megahertz. 10 megahertz. Inside, so it's a wide band. It covers so many frequency components. Okay, beyond it is covering the frequency components beyond this audio frequency. That means less than 20 hertz also it is covering, and greater than 20 kilohertz also it is covering, this wideband amplifier. Understand? So wideband amplifier actually amplifies the components ranging from, say, 10 hertz to, say, 10 megahertz frequency. And understand, that's wideband. And radio frequency, yeah, radio frequency is giving us this narrow response, right? What does that mean? Narrow response. What it does is we can design our radio amplifiers to amplify only one signal which is there at 100 megahertz. Okay, and this is called as center frequency of naught or resonating frequency of naught. Okay, so sometimes we have the applications wherein I want only one frequency component to be amplified. And what is that frequency here? It is 100 megahertz. And if you want such frequency selective response, then we go for something called as radio frequency amplifier. This is called as frequency selective. Which frequency among all this is selected for amplification? Only 100 megahertz frequency component selected. Even we can select 100 kilohertz. If it is 100 kilohertz, then we can have a response like this. I'll rather write that here. Suppose I want to have an amplifier amplifying only one component at 100 kilohertz, then the response of radio frequency amplifier looks like that. Understand? So it is amplifying one component which is existing at 100 kilohertz, whereas here it is amplifying one frequency component which is existing at 100 megahertz. So that is what radio frequency can do. So most of the times radio frequency amplifiers are frequency selective amplifiers. So whereas all other amplifiers are amplifying the range of frequencies, whereas here it is just amplifying one particular frequency. It's not the range of frequency, it is one particular frequency as far as the radio frequency amplifier is considered, whereas all other amplifiers, what they do, they rather give the output for range of frequency. Understand? So different ranges are there for different amplifiers. For DC coupled amplifier, the range starts from 0. For audio frequency amplifier, the range starts from 20 hertz. Understand that? So for different amplifiers, there are different frequencies which are rather considered to identify the different amplifiers. Is this okay with you? Let's see what they have further to tell us regarding all this. Note that for response curves of this type, frequency is almost invariably plotted on logarithmic scale. I told you logarithm. This is logarithmic scale. So 0 gain is 1. Logarithm of 0 is 1. Logarithm to the base 10. Log to base 10. Okay, is 1. Because why do we have to go for logarithmic scale for all this frequency response? Why cannot we see? Gain means what? Let me just show you. Gain means what? Since this is voltage gain or whatever, if it is voltage gain, it is V naught by Vi, or if it is current gain, it is I naught by II. If it is what power gain, it is P naught by Pi. Whatever the gain is, if we plot this, we can even go for plotting, but instead of plotting this, we plot this. Okay, we plot 10 log V naught by Vi to base 10. Understand that this is what is logarithm scale. We convert this into this in dBs rather. Okay, so instead of calling them as logarithmic scale, we can even call them as dBs. So instead of plotting it in gain, we rather plot it in terms of gain in dBs. Okay, that is why they call it as logarithmic scale. Why we have to do it in logarithmic scale? Because here, if we do it in logarithmic scale, we have a smooth response like this. We have a smooth response like this. Or else we can have a response like this, which is not smooth enough. Understand? Or we may have a glitch here somewhere, or somewhere we can have a response like this. Understand? So if you want a smooth response, then we go for logarithmic scale. Understand now why we should go for logarithmic scale now? Fine. Then the frequency response of the amplifier is usually specified in terms of upper and lower cutoff frequencies. This I didn't discuss. So this we shall discuss. Okay, what is upper cutoff frequency, what is lower cutoff frequency has to be discussed. We shall discuss that in the next slide. Okay, so here upper and lower cutoff frequencies. So without this upper and lower cutoff frequencies, this frequency response is actually incomplete. Understand? We shall see how that is. We shall see how that is. Fine. In the next slide, I'll be talking about this upper cutoff and lower cutoff frequencies. Fine. Now, the frequency response of all these are frequency response of an amplifier is usually specified in terms of upper and lower cutoff frequencies. What again, the same thing came. The frequencies are those at which the output power has dropped to 50%, otherwise known as minus 3 dB points, or where the voltage gain has dropped to 70.7% of mid-band value. So this you will not understand unless I give you some points now. Okay, so let me take those points here. Now, I'll take that in more detail. Now, see here, this F1 and F2 are called as upper cutoff. This F2 is upper cutoff and F1 is lower cutoff frequencies. Without this, this is not complete. This frequency response is not complete. Okay, and when we measure this upper cutoff and lower cutoff frequencies, what we do is we rather don't measure that upper cutoff here. We are not measuring it here. No, we are not measuring it here. Rather, what we are doing, we come down by 3 dB. So that means minus 3 dB is what we come down by. Here also, we come down by minus 3 dB. What is this minus 3 dB? We have to understand. Okay, minus 3 dB means it is multiplying the maximum voltage by 0.707. Understand what I mean? Everybody just understand. This is the power gain they have plotted. They have plotted the power gain. Okay, here they have plotted the voltage gain. Okay, if it is voltage gain, when we come down by 3 dB, it is 0.787 times the maximum value. And if it is power gain, when we come down by minus 3 dB, it is actually half the maximum power. It is 0.707 times the maximum voltage gain. Here it is half the maximum voltage, maximum power gain. Understand that? Why it is so? We shall try understand. I'll explain you again. Just lend your ears here very carefully. We shall take a frequency response. Okay, so it comes like this. Fine, and this is voltage gain. Voltage gain means this is the maximum value of voltage gain. AV max. AV max is what? This is AV max here that I have given. This is voltage gain AV, voltage gain AV, and this is the maximum value of voltage gain that I've written here. Is that okay? Now I have to identify F1 and F2. I have to identify F1 and F2 means I have to come down by 3 dB. That means I have to come down here by 3 dB. Since I'm coming down by 3 dB, I say it is minus 3 dB. So from maximum, I'm coming down, right? So it is minus 3 dB. When you come down by 3 dB, you will have 2 points intersecting the response here. One is at frequency 1, the other one is at frequency 2. So see here, you have 2 points of intersect when you come down by 3 dB. Okay, so that is F1 and F2. And when you come down by 3 dB, this point, if this is maximum of the voltage gain, this point would be 0.707 times the AV max. What is 0.707 times? Means here, 0.707 times means at F1 and F2. What would be the gain? The gain would be, okay, 1 by root 2 times AV max, or this is actually equal to 0.707 times AV max. Everybody understand that? This is 1 by root 2 or it is 0.707 if you are taking the voltage gain. If you take the current gain, then also it is 1 by root 2 AI max because it is current gain, or 0.707 times the current gain, AI max. Understand this? Now, what is power? Power is V into I. Okay, so therefore at F1 and F2, this power would be what? 1 by root 2 times AV max and into 1 by root 2 times AI max. What is 1 by root 2 into 1 by root 2? Can you tell me? What is 1 by root 2 into 1 by root 2?
1 by 2.
1 by 2.
1 by 2. Then we have AV max into AI max. And what is AV max into AI max? According to the gain that we have seen in the last class, it would be half times gain. Okay, so A, instead of writing this, we can rather do this. Half times power gain. Okay, that is what is this. So if you come down by 3 dB for power, it is half the power. For currents and voltages, it is 0.7 times 0.707 times the maximum. Is this understood? That is what in the previous slide they are saying. These frequencies are those at which the output power has dropped by 50%. That means 1 by 2 dropped by 50%, otherwise known as minus 3 dB points. For the power, it is power drops by 50%, whereas the voltage drops by 70.7%. 70.7% means here 0.707 into 100. So that is 70.7%. Okay, so for voltage it is 70.7%, whereas for power it is 50%. You understand now how it is? Is this clear to you, everybody? Why for power it reduces by half. Why for voltage it reduces by 0.707. If it is 0.707 for voltage, for current also it would be 0.707 times the maximum. Okay, so that is this. At F1 and F2, it is 0.707 times for voltage gain and 0.707 times for current gain, and power is voltage into current. So at F1 and F2, power would be 1 by root 2 times AV max and 1 by root 2 times AI max, which actually gives half the power. Okay, so for power it is 50% reduction. For voltage it is 70.7 times reduction percentage. 50% and 70.7% for voltage gain. Is this understood now, everybody?